Hi, I'm Collin, the Chief Technologist for ZKX Solutions. In the wake of the news that we've just recently been awarded a patent for our disruptive and novel multi-factor authentication technology, we wanted to take this opportunity to formally explain what it is that's contained in our patent and what exactly makes us so unique and powerful. In short, in the ZKX multi-factor authentication scheme, private user authentication data is never stored, either on the server end or on any kind of client credential or device. Similarly, we're leveraging something known as a zero-knowledge proof, or just a more secure way to communicate private information from a client to a server in order to drive both interactive and non-interactive forms of this multi-factor authentication. Every authentication platform needs to be able to handle two primary modes of operations. The first being enrollment, or the act of tying a user to some kind of digital identity or specific credential, but in the ZKX system, we consider not just the user for this enrollment process, but also the specific device which they are employing. On the server end, we have our ZKX multi-factor authentication enrollment server that's responsible for more of the computer operations of ZKX enrollment. The most fundamental one being the derivation of cryptographic key material. So this enrollment center is primarily responsible for generating public and private key pairs in some number or volume. These public keys, denoted here in black, and the private keys denoted here in red. For the public keys, these keys are sent off to some database that lives somewhere in the organization's network or network infrastructure. These public keys are associated with this specific user device and whatever identifiers the organization is using to verify or identify this user and device pair whenever they need to be authenticated later on. This user is expected to have some kind of authentication credential data with them. For the purposes of this exercise, we're going to assume that this user already has a PIN number, a password, and then some kind of scannable RFID or NFC token. These user credentials are supplied to the enrollment center by the user in an interactive fashion, and these credentials are used to transform these private keys, again, that were issued by the enrollment server, into cryptographically inert objects or data that are not inherently authenticating or sensitive on their own, in forms that we reference as device fragments. So this user credential data is applied to these derived private keys, again, derived by the enrollment center using standard cryptographic key generation functions. These derived device fragments here are then stored on this specific user device. At the conclusion of enrollment, these private keys are then destroyed by the enrollment center. So the only pieces of data we have left in our information ecosystem are the public mates to those private keys that are stored in a database somewhere within the organization's network, these device fragments, which again are not inherently secretive or authenticating on their own, that are stored on the user's device, and the user credential data, which is information that they're always expected to have and will need to be able to reproduce at the next phase of operations, authentication. So now that our user and device have been enrolled, we can look at how they are authenticated. Again, on the client side of this transaction, we have that same enrolled user using that same enrolled device. The user in question, again, still has that same credential data that they're always expected to have on them. Here, it's that PIN, that password, and that scannable something that's a physical token that belongs to them. As a consequence of our enrollment, we know that this device is now storing these device fragments. Again, non-authenticating, non-secretive information that belongs specifically to this user's device. On the server end, instead of our enrollment center now, we have the ZKX authentication server, which is going to be responsible for reading that user and device public information, again in the form of their public keys, in issuing authentication challenges to this user and device based off of that stored public information. So the workflow goes something like this. Authentication is not very useful if it doesn't have anything to protect. So we have to presume the existence of some sensitive resource that lives in the network environment that this user and device have exposure to. Let's say that this user, utilizing this specific device, wants access to this specific resource in question. This specific resource has an access policy attached to it that says before any user on any device can access this particular resource, they need to successfully pass multi-factor authentication, in this case, ZKX multi-factor authentication. This server, knowing that this user and device do indeed have public information associated with their identity, is going to reference that public information from that database that's on the network infrastructure. After reading that public information that belongs to this user and their device, the server will then issue an authentication challenge. Essentially, this challenge is saying, I know what your supposed public information should be for this user utilizing this specific device, and I need you to prove to me that you have the private equivalence of the public information I have access to. The problem here is that that private information was destroyed at the conclusion of enrollment. So one of the core cornerstones of what makes the ZKX technology in our patent so novel and so powerful is that we can recreate that private data from elements that are not inherently sensitive. So in this form, we're going to use those same user credentials, but instead of applying them to the private keys like we did in enrollment, we're actually going to apply them directly to these device fragments here. With the same mathematical operations in play, we're now able to recreate those private keys that correspond to the public keys that are being used as the basis for my server's authentication challenge to this user and device here. These private keys, we can't just send them over to the server to prove their existence, right? That would be totally insecure. So these private keys are going to be used as input to a zero-knowledge proof, which is essentially a mathematical transaction now between this user and device on the client side, the authentication server on the server side, that proves my user and device do indeed possess the private key analogs to my server's public keys without revealing any single bit, any single 1 or 0 of information about any of these private keys in particular, other than the fact that my user and device do indeed possess them. Using this methodology, the server becomes sufficiently convinced that my user and device do indeed have the correct private information that corresponds to its own public information. These private keys are then destroyed once more, and we're left with, in our information ecosystem, once again, just that public key information, that user credential data, and these non-sensitive, non-authenticating device fragments. This interactive authentication extends also to a non-interactive version of this same zero-knowledge proof-driven authentication. The primary difference being, here in the interactive version, the user has to interact with the system by supplying their user credential information. In the non-interactive system, the user does not interact with the system, does not input any new credential data, but they are still able to be continually authenticated using this zero-knowledge proof-driven methodology. By combining these two novel technologies, we were able to be awarded a patent that really capitalizes how disruptive and unique this security technology actually is. For the zero-knowledge proofs, we do have added content and more video content specifically on how these zero-knowledge proofs are operating. That will be linked on our website underneath this video.